dielectrics. Ready for the next set of questions? Let's put all this one in. Okay. Is the charge still the same or changed?
Change.
Why would it? Or what would it be?
Because there's water.
There is water? Uh-huh.
That's what. Kappa.
Yeah, so will the water allow charge to go from here to here across? It's an
No.
insulator, pure water.
Oh.
Yeah, so the charge should still be whatever you started with. Remember, a dielectric is an insulator. Does not allow charge to flow through it, so the Q is still the same. Plus Q minus Q, and it's still 800 nano coulombs. Charge is still the same. But next, how about V?
Is not.
V naught over kappa. Right? So V naught is 1/6 over 80. You get 2 volts. How about C? Good. K times C naught. So kappa is 80, and C naught was 5, right? So 80 times 5. 5 nanofarads. So 400, right? 400 nanofarads. And then U, the potential energy now. Potential energy stored would be what? Like this. Okay. So we get 1/2. C is 400 times 10 to the minus 1 times V, which is 2. We have to just do it. I get 8 times 10 to the minus 7.
When I did this, I looked at the U equation and I kind of kept in mind that C was going to be greater by a factor of 80, V was going to be smaller by a factor of 80. So I kind of just divided the initial potential by 80. That's
right.
Okay.
It would just end up the initial over 80, over capital.
Perfect. Thank you.
Yeah. Let's do a slightly different problem. Stay with the dielectric. And this will be the last problem in this chapter before we go to the next one. So let's do it. Start here. Can I erase this?
Yes.
Yes. And then so here is this example. I like this example because it combines a few concepts.
Professor, I want to ask what C indicates. What is C?
C? Capacitance?
Yeah, I mean like how do I say?
It's the amount of charge you can hold per voltage.
Oh, the amount of charges.
Yeah, it's Q over V.
So by like immersed in the water, the amount of charge that the capacitors can hold is much bigger.
It's increased, yeah. Yeah. Yes.
When you increase your dielectric constant, your voltage goes down, but your capacitance goes up.
Yeah.
Doesn't that equal the same thing as if you had just kept it the same temperature? Because if it's the charge for voltage,
What is the energy
then
stored?
if you're increasing one,
The energy stored.
Now, think about it like if you fill it up with water.
Then
So earlier,
what's
without the
lower?
dielectric,
So I took capacitors.
without the dielectric, you need 160 volts to hold this much charge. With the dielectric, you only need 2 volts to hold the same amount of charge.
okay.
Let's look at this one. Please stay focused with me on this next one, because it involves the following shape. So here is the capacitor. Here it is. Oops, kind of bent. Okay. The distance is D. This distance is D. And the area, of course, I would not keep drawing the area, but that's the area. Okay, that's the area. This is the area A. Distance is D. So you got 2 plates like this, right? And we're looking at them from the side. And we're going to put a dielectric, but the dielectric is not going to fill up the gap. It's not going to completely fill it up. It's going to occupy only this much. This way. That's the dielectric. It has kappa. And the thickness of the dielectric is T. Thickness is T. Now, the dielectric goes like this, right? It's also, it fills up, but this way. It's part of the, has the same area, but the thickness is T. Is that clear? What I'm trying to draw? You have 2 plates, and there is a dielectric between them, but it doesn't fill up the whole area. It just fills up part. So the question is, find the capacitance find the capacitance. So you need to express your answer in terms of what? What do you think? What are the relevant things?
Kappa.
Okay, so you need A, D, kappa.
T.
Yeah, the thickness of the thing, of the dielectric will probably matter, right? And what else will show up probably? Epsilon, yeah. So we need our answer in terms of this. Okay. Right? How are we going to do this? We will do it by definition, and then I will show you a little trick that we can do it with, which will help us solve more complicated problems. So we'll do the definition first. The definition is this. So we'll do the definition. Definition of capacitance is C is the charge divided by the potential difference, right? The charge, so we got this is plus Q, and then here you would have minus Q, right? On the bottom plate. And the question is, find the potential difference between the 2 plates, and then divide the charge over that potential difference, and that's your capacitance. Okay. So what's the potential difference? Let's think about it. I have 2 plates here, so the electric field due to the plates is E, or E naught if you like. It is Q over epsilon naught times the area, isn't it?
Mm-hmm.
Yes, that's the electric. Now, what would the electric field inside here be? Inside this? Inside here. The electric field here would be something like this, but it would be what? How much would it be? Yes. E naught over kappa. Will be reduced by a certain factor, yes?
Is the G for the thickness of the capacitance?
Yeah, of the dielectric.
Oh.
This is the dielectric. This is the plate. These are the capacitor plates.
Oh, there.
So what's the potential difference? Okay. What's the potential here at the negative plate?
Zero.
That would be zero, right?
Mhm.
The negative plate, that's the zero.
Mm-hmm.
And then we want to find the potential at the positive plate. So what's the change in potential in going from here to here? Let's name this distance. Let's give it the name A, and then it would go away. A would replace it. And then from here to here, let's name it B, just as an intermediate step. So what would be the potential difference from here to here? Let's call it VA. The potential difference from here all the way here would be VA plus V inside the dielectric plus V from here to here. That would be the total potential difference. So it would be VA plus V through the thickness T plus V through the change of V. Okay? Okay. So who can tell me what VA is in terms of the electric field?
E naught B, E naught A.
Yeah, it will be electric field times distance, and then yeah, we will substitute the Q and stuff like that. But for now, it's E naught A, right?
Mm-hmm.
How about through the dielectric?
E dielectric times
Okay.
T.
Okay, so it will be the electric field in the dielectric, which is over kappa times T, right?
Mm-hmm.
Okay, how about B?
E naught B.
Okay, good. We factor E naught, so I have A plus B plus 1 over kappa times T times E naught. What's A plus B in terms of D and T?
D minus
Yeah, D minus T is equal to
T.
A plus B, right? D is the whole thing. If I take away B and A, I will just be left with T. Yeah. So this is just D minus T plus 1 over kappa times T times E naught. Well, what's E naught? There, Q over epsilon naught A, right?
Mm-hmm.
Q over epsilon naught times the area. And then I would have D, make square brackets. Minus, I'm going to factor T. So it would be T times 1 minus 1 over kappa.
Q over epsilon naught T.
And U over epsilon minus T. Okay, that's V, right? That's the potential difference. Now we can find Q. We can find C. I just have to do Q divided by all this, right? So let's find C. C will be yeah, Q over V. But notice when you do Q divided by all this, the Q cancels, right? And you just have epsilon naught A on top, and then this epsilon naught A, and then the stuff on the bottom. E minus T times 1 minus 1 over kappa. So this is going by definition, and that's what it gives us. We'll do it differently, but I want to reflect on it first. We'll do it in a different way in a moment. So, right, C is Q over B. And what does B mean? The potential difference between the two plates, right? From the negative plate to the positive plate.
You can just split it up like that, though, like it's not, like I don't know that there's a similarity between it and like in series or parallel and parallel.
It is, and you see, well, remember, delta V, delta V, we can go over the detail there, but here's how you should think about it. The integral from minus to plus E dot ER, right?
And then just going out into 30.
Yes,
Oh.
so the electric field from here to here has one value, from here to here it has another one, from here to here it has another one. And it would just be added. Yeah. But, all right, so we have this. So I want to reflect on it, okay? If I didn't have a dielectric, in the absence of a dielectric, what should the capacitance be?
E naught A over D.
Epsilon naught A over D, right?
Mm-hmm.
Yeah. If there is no dielectric at all. So let's reflect on it. So here's the first note. If the thickness goes to 0, if T goes to 0, what does it mean? If the thickness of the dielectric goes to 0, it means how much dielectric do you have? No
Zero.
dielectric, yeah. So you should get that expression, right?
Mm-hmm.
If the dielectric disappears, it should reduce to this. So let's think about it. If the thickness becomes 0, I have 0 times this, that's gone. So I just have epsilon naught A over D. So I get back what I expect, right? So I just, then C will become epsilon naught A over D. Let's do the second one. If, let's say, let me ask you, what's in here? Nothing. So what's the dielectric here?
Zero.
C naught.
One. One. Remember, dielectric constant of a vacuum is one,
Oh yeah.
or air. So if the dielectric, if the kappa becomes one, so basically this becomes the same as this and this, right? So the dielectric has disappeared again. We should get what? This, right? We should again get epsilon naught A over D. Let's see if that's the case. If kappa is 1, 1 over 1 is 1, 1 minus 1 is 0, and then 0 times T you get 0, so you just get epsilon naught A over D. Okay? Number 3. What if the thickness becomes equal to D? Meaning, if the thickness becomes equal to D, it means the dielectric is filling up the entire thing, right? It fills up the entire thing. What should the capacitance become? It should become, without doing any calculation,
J times.
kappa times all this, right?
Yeah.
If it fills up the space. So let's see. If T becomes D, so let's see. If T gets replaced by D, you'll have D times 1, right?
Yeah.
That's 1, so D minus D is 0, and then you would have, so basically D over kappa flips, you get kappa on top and D on the bottom. So it becomes, yeah.
What are the, sorry, what are the hypotheticals for? I'm a little confused on that.
The hypotheticals?
Yes.
Yeah. So, yeah.
No, I'm sorry, you said it as if, T is, 0.
Yeah.
I was just confused on the general concept.
So we're asking in limiting cases. So we said the problem says I have a dielectric, right?
Yeah.
Of a certain thickness. So I'm asking the question: if the dielectric disappears, right? If I have no dielectric anymore, what do I expect the capacitance to become?
Gotcha.
It should reduce. I should get this. This is the capacitance without a dielectric.
Gotcha.
So I asked if the thickness becomes 0, meaning I have no dielectric anymore, and it does reduce to this. Yeah.
And the central kappa for the vacuum is 1.
Yeah. Not 0. 1. And is it clear now? The other.
Yeah, sorry.
Okay, yeah. So if the thickness becomes D, you will notice this. The capacitance becomes kappa times epsilon naught A over D as it should. Now I'm going to show you the second, the other approach, which should help you solve these types of problems. So the other approach is this. I'm going to draw it on the board here. We can view these as three capacitors in series. Capacitor followed by another one followed by another one. I can view them this way. A capacitor, let's call it C1, followed by C2, followed by C3. And then we can ask what's the equivalent. The equivalent will be adding the reciprocals and then taking the reciprocal. So let's think about C1. C1 will be epsilon naught times the area over, well, C1 has nothing inside, right? But what's the thickness of C1? Or what's the distance for C1? B, right? So it'll be epsilon naught A over what? B. So, again, just, what are we trying to do here? A different way of solving the same problem. So here's a different approach of solving the same problem. I'm saying earlier, we used the definition of capacitance to find the total capacitance. Here, we can view these as three separate capacitors and then see if that approach gives the same thing. So this is the justification of why we can do this. So the area is A, right? Each of them has an area A. So that's the capacitance here. Let's look at capacitor 3 next, and then I will leave the number 2 in the middle. Number 2 is the one that has the dielectric. This one is the one that has kappa. C2 is what? Epsilon naught times the area over what?
A.
Over A, right?
Yeah.
The distance is A.
Isn't it T? It's kappa.
C3? Oh,
Oh, 3.
3. Let's do 2. Okay. I did 1 and 3 because they don't involve kappa. And then let's do 2. It would be epsilon naught times the area over what? What's the distance?
T.
T. The thickness is T. But it has a dielectric, so you multiply by kappa, right? Okay? That's that. So what's the total capacitance? What's the equivalent? They're in series, so what do I do? Get 1 over C, equal to 1 over C1, plus 1 over C2, plus 1 over C3. 1 over this one becomes what? B over epsilon naught A. That's 1 over C, or the equivalent capacitance. We gotta do some more algebra and then we get the same thing. So that 1 over C is equal to, all of them, they have this epsilon naught A, so let's factor it. So put epsilon naught A times B plus A, and then plus T over kappa. Again, what's B plus A?
D minus
1 minus.
Yeah, D minus E, right? Would be right? So that's 1 over C. So C would become what? You have to do the reciprocal with both sides. So you get epsilon naught times A over B minus T times 1 minus 1 over. The same. we're ready for the next show. Uh, just one final word on this one. Can I erase here? Good. So, for example, you can try it. I know we haven't finished that worksheet, but you can try it. I have different dielectrics. So in light of this, so I'm going to erase here. I'm going to ask you, following. Let's see if you, so let's say I have a capacitor here. This is a capacitor. And you fill it up, so the area is A, the area is A, and the distance is D. Let's say you fill it up with dielectrics, but you fill it up this way. So let's say you got kappa 1, kappa 2, and kappa 3. How would you find the capacitance here? Good. So you would have this one and this one are in what kind of connection? You can view them as
Parallel?
series. So here's the battery. Right? Yeah, these are in series, and these two are in parallel with this one. So that's how you can do it. Because the potential difference from here to here is the same as from here to here. So these are in parallel with this one. These two are in series. Anyway, let's save this one for the worksheet. If you have free time in the weekend, then why do it?
Our batteries died.
Huh?
Our batteries died.
Can you say it again? I couldn't hear you.
Our batteries died.
Dielectric?
Yes.
Battery is a potential source. So the dielectric is some insulating material. There's some insulating material. Huh?
A battery would not have insulating material.
They might. I don't know what it's made of. So, yeah. Could be. Okay, so let's go to the next one. We're going to talk about current next. So let me erase all this and then we'll get to it. I guess I will pause the recording instead of recording.